Okay, let's go with example number 5 from the optimization section. And in this one, we've got two things that are going to go on at different rates. It says in a swimming and running biathlon, Jill must get to a point on the other side of a 50-meter wide river. So here's our river that's 50 meters wide. And it is 100 meters downstream from her starting point. And I see here is Jill's starting point. And so this distance here downriver would be 100 meters. She can swim at a rate of 2 meters per second and run at a rate of 5 meters per second. Toward what point on the opposite side of the river should Jill swim in order to minimize? So what we have is Jill doing her swim across the river. Well, there's going to be a point that's most efficient. How far down should she swim? Or maybe she just go straight across and do the 50 meters and then do the complete run of 100 meters. So with a little bit of calculus, we actually can come up with the best point P that she should head towards as she swims this section and then runs this section. So P is the point that we're going to mark off, which would really be, if I consider that this is a full 100 meters along here, let's have her swim X meters to the point that is X meters downstream. Her actual swimming length will be the hypotenuse of that right triangle, and then she'll run the remaining portion of this, which would be 100 minus X. Okay? That's kind of the idea behind here. So we have a couple constraints. One of the constraints is the fact that she can swim at a rate of 2 meters per second. So her swimming rate, let's call it R sub swim, is equal to 2 meters per second. Her rate that she can run, R sub run, is 5 meters per second. Whoops, that almost looks like a 5. Well, those are a couple constraints. And we've got the 50-meter wide river, the 100 meters downstream. Those are really going to act as constraints or requirements in this problem. Toward what opposite point, opposite the side of the river, should Jim swim in order to minimize her time? So what are we trying to optimize here? The time. We want to minimize time. Notice a problem here, guys? If time is what we're after, and this stuff is a rate, I got to do some conversions here, right? I need to get rates converted over to time. Well, that's going to stretch back to a little bit of physics knowledge, right? We know in physics that distance equals rate times time. So if I solve for t, I would know that time is equal to distance divided by rate. Okay, so what I want to do then is get this time feature to be minimized, but time is going to equal the time spent swimming, so time sub swim, plus the time spent running, so time sub run. I'd love to get an equation that represents that. Well, we can do that by using, we know the rates of each. I just need to know the distance. Okay, so we got to find distance. Let's go after it. I have a distance for the run. This would be the distance for the run, 100 minus x. Can we get the distance for the swimming, which is the hypotenuse difference, or distance? So I think we've got 50 and an x, so this will be Pythagorean theorem, won't it? Let's calculate out that distance. I think I'll do it right here. So the distance will be the swimming distance. Let's call it y. Y squared equals leg squared plus x squared. the other leg. And then y would be the positive root of 2,500 plus x squared. Okay, so that's the distance swimming, which allows us then to get a time for swimming. T equals, the time for swimming is going to be a distance, excuse me, I just needed a distance divided by rate. A distance for swimming, square root, 2,500 plus x squared, divided by the rate at which we can swim, which was 2, or that Jill can swim. Add on to that the time for running, and the distance for running would be 100 minus x. So we take d divided by r. D divided by r, there's the 5. And that will get us set up. You could, let's take a derivative. Do we want to do derivative by hand? I suppose we can. Derivative. We also could allow the calculator to do it, couldn't we? Okay, the derivative. Let's go. dt dx, you could go t prime, is equal to the derivative of this. Remember, this would have been a 1/2 power. So the 1/2 power is going to come down. I have 1/2 coming down, but I already have a 2 there as well. And then square root, this will go to, if I subtract 1 in my derivative process, it'll go to a negative 1/2, so that's going to drop the square root to the bottom. Now don't forget to do a chain rule, so the derivative of the inside becomes 2x. There's the derivative of the first section. Next section, let's reword the 100 minus x into 100 minus x could be written as 100 divided by 5 minus x divided by 5, so a 1/5 x. And that will make a plus 0 minus a 1/5 in our derivative. Okay, let's simplify dt dx. dt dx is going to be an x over 2 root 2,500 minus x squared minus a 1/5. Cool. We want to optimize by minimizing the time. So our next step comes in. We want to find our critical points. And the way to do that is to set 0 equal to this, right? Problem is, this looks like it'd be kind of interesting to get the value out. 2,500 minus x squared minus 1/5. So let's use the calculator to do that. Okay, so hopefully you've got the equation loaded in your calculator. If not, why don't you hit pause and get that accomplished. I am going, so this is the derivative function. I'm looking for where it equals 0. Correct? That's what we're after, the critical points. So I'm going to go ahead and maybe just zoom 6 it. Ew, that doesn't look very good. So I assume that this is going to cross over eventually as we go to the right. Maybe I'm going to try a zoom 0 just for that zoom fit. Oops, I might have screwed it up. I don't think I did. I think I hit an extra enter. All right, let's hit clear and then zoom and a 0. There it goes. So I get where it's intersecting. I'm going to look at my window. So my x min is -10 to +10. I don't really need to see the negative distance because I know from my application that x is going to be positive. So I think I'm going to shift this a little bit to maybe -2 to positive 20, 25. And then let's Let's see, y min, that's probably fine. Let's just, oh, something's not snapping here. I needed to shift this. I want to see above it, and I want to see below it a little bit. It's really ultra tight. Let's try that. Okay, that's a little better. I'm still way out here, so maybe a little bit more window work. Let's take this to 27. Let's narrow our, into kind of zooming in on our y values a bit more. And 0.5, but that needed to be a negative, darn it. All right, graph. Okay, I can find where that crosses. So now I'm going to second calculate, get that 0 calculated. Moves kind of slowly because we're all at like 20, 25. Close enough. And quit. I think I would trace 20. I know it crosses over around 21. So I'm gonna hit second calculate my 0. I was not far enough behind it on the left side last time, so I missed the 0, and then I'm gonna stop about there. Now, are you kidding me? Let me start over again, guys. I'm screwing this up. Left bound, I want to be around 20-ish. Enter. Right bound, I want to be about 22, 23. Okay, that should. Let's visually go a little bit more. Okay, I think I got it this time. Third time's charm. 21. Where's my x min? My critical point is occurring at x equals 21.822. And that, I think, will answer the question, toward what point on the opposite side of the river should Jill swim in order to minimize her total time? So according to our diagram, we want P to be 21.822 units from her starting point, right? Horizontally from her starting point, but directly across the river. That's how those problems go. They're kind of cool problems. A little more difficult just because you've got to get that time element in there as well. All right, have a good day. We will go back to example 4 when we come back on Monday and capture that problem. So homework is to do the worksheet 1 through 4 on the front side, which is optimization, and backside is good old review. See you later. Over and out.